Hey everybody. Part one of this lecture was brought to an unfortunate conclusion. It ended much too quickly, so we're resuming now. And the division theorems that we looked at in the part one of this video can be used to show the fundamental theorem of arithmetic. And here's what the fundamental theorem of arithmetic says. Every positive integer n greater than 1 can be expressed as the product of primes. Every positive integer greater than 1 can be expressed as the product of primes. This representation is unique up to the order of the primes. In other words, if we don't take into consideration the order in which the primes occur, then the representation is unique. Every positive integer, n greater than 1, can be expressed as the product of primes, and there's only one way that this can be done, disregarding the order of the primes. Here's a corollary to the fundamental theorem of arithmetic. Every integer n greater than 1 has a canonical representation, or generally accepted and or preferred representation, as a product of primes. N equals prime number 1 to the power of k1, prime number 2 to the power of k2, etc., where p1 is the least of the primes, p2 next to the least, and so forth. Let's consider a quick example, 4,200. This is actually pretty easy because it's 100 times something. 6 times 7 is 42. Okay, let's go with that. Yeah, 6 is 2 times 3. And 100 is 2 squared times 5. No, 2 squared times 5 squared. In canonical form, we list the primes from least to greatest. And we have 3 factors of 2, 1 factor of 3, 2 factors of 5, 1 factor of 7. And we can either put it in this form or this form. Where those primes without explicit exponents are assumed to have an exponent of 1. So this is canonical representation as the product of primes. I have this in my notes next. I'm not sure why, but maybe if I do this and then go a bit further, I'll remember why I had this in my notes. A real number r is said to be rational exactly when it can be expressed as a quotient of integers. All other real numbers are said to be irrational. And And now we're going to prove the theorem. Square root of 2 is irrational. So let's do that. It's a proof by contradiction. Suppose, for the sake of deriving a contradiction, square root of 2 is rational. It's a proof by contradiction, so we assume the exact opposite of what we want to prove. And of course, n is not 0. And m is not 0 either. If m is 0, then that's saying that square root of 2 is equal to 0. That's not true. And if n is 0, then the number is not defined. Okay? Now I'll use this catchphrase. We see it in mathematics. Without loss of generality, let's see, m and n are relatively prime. If m and n were not relatively prime, we would reduce to lowest terms. We'd cancel out common factors in numerator and denominator. So what the heck? Let's just assume they have no factors in common. M and n are relatively prime. Let's see where that gets us. Let's continue. We had square root of 2 is equal to m over n, where m and n are relatively prime. And for lack of anything better to do, we square both sides. And multiply both sides by n. This means that 2 is a factor of m squared. But m squared, that's just m times m. Now remember, we just had a theorem not too long ago that said if we have a prime divisor and it divides the product of two numbers, it has to divide one of them. Since 2 is prime and it divides the product of these two numbers, 2 has to divide one of them. In this case, both of them. So 2 divides n. Well, what does that tell us? It tells us that m equals 2k for some integer, actually some natural number, k. Okay. Now let me give this equation, let me give this statement a name. No, maybe I better not. Let me give this a name. I'll call it equation 1. Two n squared is equal to m squared, but m is 2k. I do believe I can divide both sides by 2 here. And oh, what do you know? 2 divides n squared. Which means 2 divides n times n. We have a prime number 2 dividing n times n. This prime number has to divide one of these two factors. So that means 2 divides n. Holy moly. And that means that n equals, what? A, B, C, D, E, F, G, H. Okay, let's say 2H, where H is an integer. Something's not right here. Actually, it's perfect. It's not right in the sense that we're very well poised to get our contradiction. M is equal to 2k. N is equal to 2h. What's the problem with that? What's the problem with that? They're not relatively prime. we get our contradiction. We got our contradiction. Now, what caused that contradiction? The assumption that square root of 2 is rational. Since the assumption that square root of 2 is rational led to this contradiction, the assumption must be false. Hence, square root of 2 is irrational. End of proof. Here's a good theorem. And what makes it a good theorem is that it's very useful when we're testing large numbers for primeness. If we're trying to determine whether a large natural number is prime, this sort of makes it easy for us. It prevents us or keeps us from having to look for candidates of factorization where they don't exist. And the theorem says if n greater than 1 is composite, then n has a prime factor less than or equal to its own square root. If n is composite, it has a prime factor less than or equal to its own square root. Now, what are the consequences of that? Well, what's 100 squared? 10,000? So let's say we had a number like 9,767 or something like that, and we wanted to determine if it were prime. The square root of 9,767 is less than the square root of 10,000. So in other words, the square root of 9,767, if it is composite, must have a prime factor less than 100. So if we go through the prime factors, if we go through the prime numbers less than 100, and they're not a factor of 9,767, the number's prime. We don't have to look for divisors larger than its own square root. And that's sort of what the contrapositive of this says. The contrapositive of this statement says, if n has no prime factor less than or equal to its own square root, then n is prime. So if we have a number that's less than 10,000, and that number doesn't have a prime factor less than its square root, which is less than 100, it's prime. That's very helpful. We don't mind too much testing a number for divisibility using the prime factors less than 100. It'll take a minute or so, but that's all it'll take. So this is a helpful theorem. Now let's prove it. Okay, everybody, let's get into this proof. Suppose that n is composite. Then there exist natural numbers b and c, neither of which is 1, such that b times c is n. If n is a perfect square, b and c may be one and the same. Yeah, if n were 100, b and c could both be 10, for example. Now, without loss of generality, we'll assume that b is less than or equal to c. What does without loss of generality mean? It means if we make this assumption, it in no way compromises the legitimacy of the proof. So without loss of generality, without compromising the validity of the proof, we can assume B is less than or equal to C. One of them's got to be less than or equal to the other, right? Take any two real numbers, one of them is less than or equal to the other. In this case, we just decided B would be the lesser. Now we take this inequality and we multiply both sides by B. So we get B squared less than or equal to B times C. And boy, that looks like, this looks highly relevant for some reason or other. I beg your pardon, have I seen you somewhere before? Oh, right up here. B times C is a factorization of n. Okay. Now, it looks like we're done, but we're not quite done. We've shown that square root of n is equal to b. But what we were saying was n has a prime factor less than its own square root. B is a factor of n. It is less than or equal to square root of n, but is it prime? There's nothing that we said here that would guarantee that B is prime. So we have to take care of that detail and then we'll be done. Okay, remember, we found a factor of n less than the square root of n. Our theorem claims that we can find a prime factor of n less than square root of n. Well, is B that prime factor? Maybe, maybe not. By the fundamental theorem of arithmetic, B has at least one prime factor, P. B might be that prime factor. In the case in which B is prime, then P is equal to B. If B is not prime, it does have a prime factor, P. And P is going to be less than or equal to B, which is less than or equal to the square root of n. So if B is prime, these two are one and the same. If B is not prime, it has a prime factor P, which is less than itself. And we have that P is a prime factor of n that is less than or equal to the square root of n. So every composite number has a prime factor less than or equal to its own square root.